All right, so first of all, somebody asked over email the difference between instantaneous angular velocity and average angular velocity. Don't write this down because you're not going to see it on the test, but I just want to make that clear. We did make this definition of how average is theta final minus theta initial over delta t, and then that omega, was the velocity at a particular instant in time, and we saw that in chapter d theta dt. We saw that in chapter 2, but like in this chapter, I'm not going to ask you about the average velocity. I was just setting that up as a definition to define what is our instantaneous velocity. So anytime I'm asking you the velocity, the angular velocity, it's at a particular instant in time. That's what the instantaneous is, okay? So you're not going to see that. I'm not going to ask you to calculate the average velocity. But you probably do need to know that omega is theta over t, but that's really just a special case of this equation. Omega naught t plus 1/2 alpha t squared. A special case where alpha is equal to 0, so this term goes away, and then this equation is this equation, just solve for omega. You'll see that, right? We lose the naught because omega is constant when alpha is 0. Okay? I want to do the free response. So there are 3 free response, and I sort of think of them in terms of kinematics, although there's also some Newton's second law stuff in there as well. The second one is Newton's second law. And then the third one is going to be conservation momentum, of angular momentum, or angry mom. Okay, so kinematics, you're going to have some object, let's say that it's a bar. I don't know what it'll be, but it'll rotate. I mean, I do know. It'll be a bar, it'll be a disc, it'll be a sphere. It doesn't really matter what it is. It's, the only thing that matters with that is how you go about calculating the moment of inertia if you need it. There will be some force applied to it, and then you'll need to answer some question about theta, omega, and or alpha. It will be a 2-step problem, I will tell you that you'll have to find some unknown quantity in order to find the other unknown quantity. Okay? Yeah, follow it. You've seen questions like that on some of the old exams, and I've done some in class before. So that'll be one part. I think there were 3 parts. There'll be a question about the work that's done, causing this object to either go from rest up to some speed or to go from some speed down to rest, slowing it down. Either one is going to be the same. To find the work is pretty easy, actually. It's just going to be the change in kinetic energy. So to find the work, I'm really just asking you to calculate the kinetic energy. So if you know omega and I, then to find that answer is just going to be 1/2 I omega squared. And then oh gosh, what was the third part? It was something about torque or force. Yeah, it was something about calculating the torque, I think. Or maybe it was calculating the force. I forget. But if you know the torque, then you can find the force is just equal to F times R times sine of theta. Okay? So it'll be something along those lines. It'll look familiar to you, except for maybe this part. We haven't had many of those, but we have done one of those questions. So just if I ask for work, what are you going to calculate? The energy, right? It's just a change in energy. The second one is going to look a lot like what we've done. We've done a bunch of these, and you'll see them on every exam. It comes at the beginning of chapter 8, and it's usually a 2-part question where you have some object, let's call it a disk. There are a couple of forces acting on it. For example, like this, with some angle there, a couple of forces acting on it. I'll ask you several questions. What is the net torque? So what is all the sum of the torques? Be careful on this that you get the clockwise or counterclockwise correct, because that is important. On this particular figure that I drew, let's see, this one is clockwise and this one is counterclockwise. So this one's a negative torque and this one's a positive torque. We can work some problems like that if you want. So first you would find the net torque. Next you would find the moment of inertia. Just look on your equation sheet with that table and you can calculate the moment of inertia. We'll go over that to sort of identify the shape here in just a second. Then apply Newton's second law, torque equals I alpha, and then I don't think there are 4 parts. I think there are actually 3 parts here. But then asking some question about, what is theta after a certain amount of time? That would be theta is omega naught t plus 1/2 alpha t squared. Or what is omega after a certain amount of time? Omega naught plus alpha t. So solving for one of those changes in displacement or angular velocity. You've done these before, so all the free response, I really love to see those big long black marks on everybody's paper, meaning that you got every part exactly right. And that's what you should be aiming for. And then the third part is the conservation of angular momentum. I think this was a part where I had 2 pieces. Let's say that it was a disk rotating about this axis. So I draw those little lines to say that it's filled in, it's not a hoop. We'll come back to that. And let's say that it's rotating at some angular velocity, and then I have a bar also that's rotating with some angular velocity, and then I bring the 2 together so that I have the disk and the bar rotating at the same rate. Okay, and so if I call this omega 1, omega 2, and this, I'll call this omega final, the way that you would do this is you would say L1 plus L2 equals L final. L1 would be I1 omega 1 plus I2 omega 2 is equal to I1 plus I2, because it's a perfectly inelastic collision, that's where they stick together, times omega final. Just like the last free response problem that we had where the 2 balls stuck together and they moved off in the same direction at the same velocity, this is identical to that, except you're dealing with, rotation instead of angular velocity. As I said in class today, if I give you this in revolutions per second, I'm pretty sure that I did, that's okay, because I'm putting in revolutions per second and I'm getting out revolutions per second. So my units will be consistent throughout. Okay? So those are the free response, kinematics, Newton's second law, and conservation of angular momentum. 100% on that, and then that'll set a good tone for the test. But there are a lot of calculations in this, so there's just a lot of numbers floating around on the page. Try to be as neat as possible with that. Some of you are neater than others, but if you're neat about your work, it really helps me to grade. And your job isn't to make me happy, but if it's easier for me to grade, it makes me happier, and then I won't give you more credit if I'm happy. Like my mood does not affect your grade, but just make it a little neat for me. It helps. Okay? Questions? Particular questions? If not, I can just scroll through and we can sort of look at questions. Julia?
I have a question about the first one.
The first free response question? Okay. Yeah, shoot.
Theta.
Yeah.
So if it's like not, this is 0, I know that. But if it's up or down, like straight, can we assume that it's 90?
Yeah. Yeah, I think, yes. So this angle, you're not talking about this theta, you're talking about the theta for the force. Okay. Yeah, so that is a perpendicular angle. This is a perpendicular angle. If the force was like this, which you've seen on some of the old exams, this is an angle that is theta equal to 0 degrees, or 180 degrees. And in that case, for this, that would give you a 0 torque. Did I answer your question?
I was looking, okay, so this question, like I was confused earlier when we were talking about this in class, and like with the circle, or the hoop, so like, does that work the same way? So like, does it work the same way here, with it, since this is straight down, we can assume that that's...
Yeah, let me draw it here, so, if I have a disc, like this. By the way, if I draw a hoop, I'm going to draw it, I'll tell you in the thing, and then I'll make it very clear that this is a hoop. So it looks like a big donut, or donut with a big hole. But if it's a disc, I'll usually put, shading along it. But I'll tell you in the text, and and if you're still unclear, raise your hand. Like I said, I probably won't tell you any information I'm not going to tell you any information that's not in the problem. If I do, I'll tell the whole class. But if you have a question to clarify, that's fine. Anyway, so this angle, that's not really straight. The moment arm, or the lever arm, the vector r, is in this direction. So we'll say that the vector r is like this, that's r. And then f, if this is f, that's the angle that I'm concerned with. But also, similarly, if I have a force that's down like this, that would also be an angle of 90 degrees. If I have an angle that's like this, then this is the angle that I'm concerned about, and that would give you that angle.
Okay.
I'll label it. Okay? On a bar, if I have a force that's like this, that is a 0 degree angle, which means no torque. Another question? Now, I want to go to the equation sheet right quick. So, our equation sheet, the students have been having trouble just equating the figures that I use with the words. So, this cylinder right here is a disk. So if I ever have you have a disk, and that would include things like merry-go-rounds, or a flywheel. A flywheel is just a big spinning disk. A flywheel, those are disks, okay? This right here would be a hoop. I usually call it a hoop, but a wheel would also be a wheel that's in the middle. This is a rod. As I told you in class, you are not going to see this on the test. And then these are our spheres. The only difference is that one is solid and one is hollow. Remember, the hollow sphere has a bigger moment of inertia than the solid sphere. Yeah?
That we talked about and we watched an online lecture on the person.
Richard Pryor,
Yes.
who's like the best comedian of the 20th century. Y'all probably don't even know Richard Pryor, do you? Because he's probably, yeah, you weren't even born yet. I'm sorry, go ahead.
The cylinder equation for him.
Yeah, we use this one because we approximated his body as a cylinder. But you're not gonna have to approximate anything. That was just for illustration.
For normal people, like when we say we're on the merry-go-round and we're adding a person onto a merry-go-round, that would be the who?
No. So if you're adding a person, so if you have a merry-go-round, oh, good question. If I have a merry-go-round and let's say it's rotating about this way, and then I get a little kid that comes over here, and he jumps on to the merry-go-round, this is different from Richard Pryor going around because the axis of rotation is different. The axis of rotation for this kid is over here. And for Richard Pryor, his axis of rotation was like through his belly button. So that's how you tell the difference. So for this kid on the merry-go-round, this is just a particle. So you treat it as a particle. Now, it looks like the same equation as a hoop, but you're really applying the definition of moment of inertia. I is the sum of mr squared. Where is that? Right here, that you're really applying that equation for the kid, because he's like a discrete particle. Anytime your object is away from the axis of rotation, that's going to be a discrete particle. You're not going to try to approximate it as a sphere or a rod or anything like that, because you're far away from the axis of rotation. There we go. Notice that all of these have an axis of rotation that is somewhere within their body. The axis of rotation is never outside of the body. Okay? All right. And the whole point of the Richard Pryor deal, the toy, was that if you have two objects that are spinning, you can find their total moment of inertia by adding up their individual moments of inertia. And that's important, for example, on the free response number 3, because you have two objects that are now spinning at the same rate, and you have to add up their moments of inertia to find the total moments of inertia, because they stick together and then they start spinning at the same rate. Okay? All right. Particular questions? Yeah, Kennedy?
I don't know which test this was, but when I was practicing for a quiz, they had a question about, like if a person's on the end of a merry-go-round or a wheel spinning, and then versus somebody that's towards the center, like they cover a different one. Like it's about either angular velocity or angular acceleration.
Yeah, let's talk about those in general. Those all come from the concept test. Right, those or some variation of them. So I like to use I'll often take those and shake them up a bit for y'all. So if I have a rigid body, this is our definition of a rigid body. Let's say, for example, a merry-go-round. Every body on the merry-go-round is rotating about the x. Everybody on the merry-go-round has the same angular velocity. Let's call this A, let's call this B. A and B both have the same angular velocity because every point rotates at the same rate. Let's say it's 1 revolution per second. Point A rotates at 1 revolution second, and so does point B. That's because it's a rigid body. They're not moving with respect to one another. They're all going around. However, the velocity at point A, the number of meters per second, it's covering a bigger circumference in the same amount of time than point B. So the velocity at point A will be bigger than the velocity at point B. So the object on the outside will have a bigger speed than the object on the inside. You've probably experienced that if you've ever been on a merry-go-round. You know, it feels like you're going faster on the outside because you are. If you walk to the center, then you're spinning around, but you don't have any linear velocity because your radius is 0. Remember, V is equal to omega R. So as R goes bigger, V gets bigger too. And then also the centripetal force. Remember, centripetal force is equal to mv squared over r. But it's also not on your equation sheet, but still a useful equation just to memorize. It's also equal to m omega squared r. So when I'm thinking about the centripetal force on a merry-go-round like this, if I look at this first equation, you know, V and R are both different for points A and B. V is big at point A, R is big at point A. So it's hard to say what happens when you go from point A to point B with that equation because you have two things changing. But in the second equation, omega is constant and m is constant. So if R goes up, that means the centripetal force also goes up. So that is to say that Fc at point A is bigger than Fc at point B, which you would sort of expect that an object moving what was I about to say? Yeah, I know. It just didn't make sense to me as the words came out. I'm sorry. No, let's just stop at that. So if R goes up, Fc goes up. Okay? Yeah. Okay? Yes. All right. What else? I can just skim through. We'll see. You know, all of these are good questions. I will say on this problem, I think I've had about 50,000 people talk to me about number 22. There was a mistake in that. I forget. The radius was asked for. The diameter was given. One of those questions about a tornado. You were one of the 50,000 people, right? No, you were about to ask. Do you want me to work it, or are you okay?
I can't work it, but you put diameter in one of them.
I know. I'm sorry. All right. This is a various kinematics questions there. Remember, some kinematics questions are in exam 3.
Is it, so if you would rate this exam, like on a...
10 times harder than any other exam. Now, it's not quite as easy as past exams 4, because exams 4 usually have chapter 9 in them. And while there's a lot of material in chapter 9, it's mostly just sort of plugging in the right equation.
But to me, all of this is basically using the same kind of concepts we
Absolutely, yeah.
It's just knowing like when what equals what and
Yeah. So I think, a lot of you have sort of figured out how this class works, like how you go about these various things, and it's because you've worked really hard, right? Um, and so if you figured that out, those previous chapters 1 through 6, then 7 and 8 should be a breeze for you.
Number 27. I have issues with like comparing the torques and the.
Yeah, and I think there are 2 ranking questions, one about moments of inertia and one about torques. So let's see, for torque, remember torque is equal to F R sine of theta. So to get the biggest torque, you need the one with the biggest force, the biggest moment arm, and angle equal to 90 degrees. So here, well, what do you think would be the biggest one? I would get rid of 4 because the force is off angle, so that minimizes my torque, and the moment arm is small. So that leaves 1, 2, and 3 as the biggest. Which do y'all think? 3 is right. The reason it's 3 is because notice 1 and 2 are both at an angle. They're angled actually to the same angle, it's just one's going one way and the other's going the other way. So 3 has the biggest torque, and well, 4 has the least torque. So A would be the right answer. Let's find another ranking problem, okay? That's a good one, but let's look at some others too. Oh, this is exams 3, that's why it's all exams 3. So, second, yeah. Here's one. It's not really a ranking problem, but you have to figure out which has the greater moment of inertia. And the axis of rotation, if an object rotates about one of these axes, then it changes how easy or difficult it is. And you're looking for moment of inertia, remember I is mr squared, that you're looking for mass that's distributed at the bigger value for r. So you want mass that's farther away, because r is squared, and so if r is big, that more greatly impacts I than if m is big. So I'm looking for my mass to be distributed far away, like the figure skater with their hands out, that their moment of inertia will then increase. So the one here that has the most mass at a farthest distance is going to be A. So you were all saying A in your head, right? Okay, let's look at some others. Okay, this is a good one. This is moments of inertia. I have 2 bars that are made into a T like this, and they're both equal length and equal mass. And then they're rotating about these various axes, A, B, C, and D. So if you imagine these bars, they're like this. For example, if I was rotating about D, it would rotate like this. You'll see that, how that rotates? And if it was rotating about C, it would rotate about this axis. And about B, it would rotate about this axis, and A, it would rotate about this axis. Which of those has more mass at bigger radii? A is right. At point A, about this axis, look, I got all this mass out here. So A is going to be the biggest moment of inertia. That's 3 of the options, right? So I'm left with only 3. And then I like to see which one is the smallest, because I find that I can often pick out the right answer. I mean, I wrote the question, so. But if I pick out the smallest, which one has the least, or the mass at the least moment arm, at the least value of R? C is right. C is right, because look, C has all this mass, first of all, that lies along the axis of rotation, so that doesn't contribute anything to the moment of inertia. And then, I'm sorry, did I say C? You said C. Yo, you said D. D is, who said D? Yeah, I changed my answer too. It's D. That if I have it along this axis of rotation, first of all, this vertical bar doesn't contribute to the moment of inertia at all because R is equal to 0. So it's just to get rid of that. And then this bar is split in half. So my mass is only going out to like R over 2. So C is the smallest. Again, C. You and your C. Whoever said that. Somebody said it. D is the smallest, so I can get rid of that one. And then, are there any that are equal? Look for symmetry in it. I don't see any of these that are identical. Okay, none of these are identical, so I can get rid of C too. So the answer is going to be B. And notice here that B and C, B has a bigger moment of inertia because I got this big rod out here. And then also I have this rod too. Those are tricky, but practice them. Okay, let's do another one. Oh, here's a Torx problem. Which of these has the bigger torque? Looking for a big force. I see a big force right here, but a short moment arm. Oh, here's a long moment arm, but a small force. Oh, so those are equal, right? Oh, good. So that gives me the answer right there. I don't even need to go further. But I could see that B has a bigger torque than A because B is at 90 degrees and A is at some angle. So when I say that it's at some angle, if I have an object and a force is applied there, if it's at an angle, that means that only a certain component of that force is actually providing a torque. Only the perpendicular component provides the torque. And so it's a smaller force that's actually causing the torque. I want another moment of inertia problem. Oh yeah, here we go. So this is just a metal or a plate that rotates about different axes. Which axis of rotation gives you more mass at bigger radii? A is right. A, look, I got A. The furthest point of mass is way out here. So A is the biggest moment of inertia. And which is the smallest? C, right. So the biggest distance I can go for C is like out to there. So C is the smallest. That gets rid of that. Are there any that are the same? Are B and D the same, or are they different? Yeah, they're the same, right? It's just the mirror image. So that's why I say like this sort of thing is, if you're good at organic, you're probably good at these sorts of questions. Because I think y'all do stuff like this, right? Look at molecules. Okay. All right, look, here's a question like you were asking about. I forget who that was. Lena, I think. Kennedy. Where you have the particle that sits out on the edge. Okay? Remember, the moment of inertia of this is the moment of inertia of a cylinder, which is 1/2 mr squared, plus the moment of inertia of a particle, which is just mr squared. And then you add those two together. Okay? This is a good example of the free response that I mentioned. Can we work through this? We might have worked through this in class today. Did we? I don't remember. Okay, let's just do it anyway. So I have a bar that it has a moment of inertia of 8. I is equal to 8. And it's rotating at 2 revolutions per second in the counterclockwise direction. So omega is equal to positive 2 revolutions per second. Remember, I don't need to convert that because I'm asking for what is the new speed. It engages with a flywheel which is just a cylinder. But I tell you what the moment of inertia is. It's equal to 16. And it has a moment of inertia of 4 revolutions per second. Omega is equal to -4. -4 because it's clockwise. Draw a picture. It'll help you to think about it. And then they come together, and they're both rotating at some rate. So I say L1 plus L2 equals L final. L1 is 8 times 2. Remember, L is equal to I omega. So 8 times 2 plus 16 times -4 equals 16 plus 8. They stick together, so they have the sum of their moments of inertia times omega final. And that's what I'm solving. So I have 16 minus 64. What's that? Is that 58? All right. Yeah, 16 minus 64. 48, right? Hang on, 48. Divided by 24 is equal to omega final. So it's -2. That would be 2 revolutions per second, and look, clockwise. I will ask you on the free response, what is the direction? And that will be part of the answer. Make sure that you get the direction. Because, like, if you don't get the direction, then it's not right. If it's not right, it's automatically half off. Okay? Elena?
So should we do like how it's like in the problem where you put a positive 2 and then you just put clockwise, or should it be like negative?
I ask you to say, is it clockwise or counterclockwise? So this would be 2 revolutions per second clockwise. Yeah, I want to know that you know that.
Just take the negative out and then 2.
Sure. Yeah. Oh, this one is fall 16. It's like a good exam. Number 7 and 8 is a good example of the free response for Newton's second law. We've already worked on that, I think. So we can do it if you want, but okay. And that's all fluids. Oh, here's a good moment of inertia. I think we worked this one in class today. Remember, the one with the most mass at larger radii is A, right? Look at all this mass out here. It's far away from the axis of rotation. You know, this has the same amount of mass at that distance, but it's missing this one. So this one has these 2 rods and this, but this one just has this rod and that, and it's missing this. So it has a moment of inertia less. And then this would be the smallest moment of inertia. While it has these 2, it doesn't have a bar out here. And the bar out here is really what would contribute to your moment of inertia, because it would have a mass out at a big radius. So that would be A, B, C, biggest to smallest. Yeah, I, B, I, C.
So it's just whatever's like farthest away, and then if the line is in like the middle of the bar, then you know that it has a 0 radius.
Yeah, so like for example right here, this part of the object doesn't contribute anything to the moment of inertia. It's really easy to spin something like this because there's no mass out at big radii, but it's really hard to spin something like this, and then it's even harder to spin something like this because I'm putting my mass out at bigger radii. It's a hard concept. A lot of people have trouble.
I think I see it now.
Yeah.
I'm kind of seeing it like a swinging door almost.
Mm-hmm. Yeah. Yeah, you can see it like a swinging door. Okay. Yeah, I was just about to do that one. Yeah. We did one similar in class today, but it was a little easier, the one in class. So it says a merry-go-round. That's a disc, but that doesn't really matter. You have a merry-go-round, a kid comes and jumps onto it, and it says that the moment of inertia doubles. Now, for the merry-go-round, L is equal to I times omega. When I double the moment of inertia, this stays the same. If the kid jumps onto the merry-go-round, is the merry-go-round going to go faster or slower? Slower, right. It's going to go slower by the same amount, by half. So I have a merry-go-round that has double the moment of inertia and half the angular momentum. Now kinetic energy, that's really what we're asking for, is 1/2 I omega squared. So I'm halving omega, doubling I, so 2 times 1/4 is equal to a half. So it's going to have half the energy that it had before. Okay? Don't forget, the quarter came about because this was squared. Huh? Who was that talking? Is that Elena? Yes. Okay.
I'm talking about that. There's one that I have no idea what's going on in. I just don't remember which one it is.
Okay. I'll continue. You'll probably have a set of discrete particles, something like this. That is just I is the sum of mr squared. All right, so you have 1 times 1 squared, 1 times 1 squared, and 4 times 2 squared. You just add all those up. Here's an object where I have a bar, and it extends to a longer length, but it keeps the same mass. I think we might have worked this one today. Y'all good on this one? Carolyn, what? Oh, this is fall 207, 2017. Want to work 6? What you got, Lane? This problem? No.
2016, exam 4, number 2. It's another energy one.
None of them are tricky. 16?
16, number 2.
Oh, yeah. This actually came directly from one of the concept test questions. I think that maybe I put a number in it. So, two objects have the same angular momentum. Object 1 is spinning twice as fast as object 2. I find it helpful to draw a picture to help me to keep the variables in mind, because I know if it's spinning twice as fast, is this going to be something with a bigger radius or a smaller radius? Smaller radius. So, like, remember the figure skater, if she has her arms out, she spins more slowly. So object 1 is going to be a small radius, object 2 is going to be a big radius. And this one has an omega, this one has an omega, this one is 2 omega, and this one is just omega. So if the energy of object 2 is 10 joules, what is the energy of object 1? I also know that their angular momentums are the same. So I omega equals I omega. If this one has twice the speed, and it has the same angular momentum as this one, that means it has half the moment of inertia. Now the energy of object 2 is 10 joules, so what is the energy of this one? Well, energy is equal to 1/2 I omega squared. Omega is twice, and I is half, so that's the energy of this one is twice the energy of this one. It has more energy, so it's going to be 20 joules, which makes sense because it's spinning faster, and energy is more dependent upon speed than it is on moments of inertia, because it's a quadratic term. Energy is more dependent upon speed. As the speed goes up, the energy goes up more. So since it's spinning faster, I could envision that it has more energy. Now it has a lower moment of inertia, but the energy term is squared, and the moment of inertia term is not. All right, that is a little tricky. I know. A lot of people have been doing that. Yeah, this is a constant. Just forget about it. Erase it, as you said. Or, yeah. Like on the test, the printed half, that's hard to erase. Though I had a student once, many, many years ago, who I gave different versions of the test, right? And he decided it would be a good idea to copy the answers from the person in front of him. But that person had a different version of the exam, and I had the version number printed on the exam, so erased, like with his fingernail, the version A number that was on there, and then I sketched in a V, which was the same version as the student. And I was watching the whole thing, of course, because I can see when y'all are up to things. And then he turned it in, had it labeled as version B, because I had a version question. I don't do different versions right now, but I had a version question, and anyway, he got a 0 on the exam. Yeah. I assume that you're honest. I know most of you are honest, right? Y'all honest? It's important, especially if you're going to be doctors and engineers or scientists or whatever it is that you're going to be. It's important that you're honest. Not worth it. We had a student expelled a number of years ago. It's just he had several academic dishonesty situations. Anyway, any other questions? No? Okay, I think we'll stop there.